Good morning, everyone. Thank you for the opportunity to present my work. Vehicle routing problems are very complex and challenging to solve. Yet, good solutions achieved in a timeliest manner are vital to the success of any supply chain. In this presentation, I shall be briefly summarizing the content of my fourth year project. I shall touch upon the background, problem and scope, the mathematical model, the exact implementation, the meta-heuristic implementation, and the subsequent case study. The SPAR Western Cape Distribution Centre was the industry partner attached to this project. Their stores are customers who must be satisfied, for which they have adopted a responsive business model. With more than 40 vehicles, they schedule about 200 deliveries on an average day, but schedule more than 300 deliveries on peak days in 2019. Vehicle routing is done by human schedulers who use daily time windows per customer as guidance. The capacitated vehicle routing problem with time windows is a variation on the oldest incarnation of the vehicle routing problem, the capacitated vehicle routing problem. Some other notable variations on the VRP presented in Toth and Vigo's vehicle routing book include the VRP with pickups and deliveries for goods, pickup and deliveries for people transportation, the stochastic VRP, the VRP with backhauls, the heterogeneous fleet VRP, the periodic VRP, the VRP with split deliveries, the VRP with profits, and the dynamic VRP. The problem addressed in the project was to derive and implement a model capable of timelessly recommending a set of high-quality routes for the SPAR Western Cape DC. Complexities that were considered within the scope for the final implementation include vehicle capacities, customer time windows, delivery unload times, the heterogeneous vehicle composition of the DC's fleet, the ability for vehicles to make multiple trips, the possibility for deliveries to customers to be split across multiple vehicles, and the expected travel time and distance between customers. Some simplifying assumptions were made. Travel time and distance estimates, as well as customer demands, were assumed to be deterministic. Travel time remains the same throughout the day. Customers may have a maximum of one time window during the period considered, and there are unlimited third-party vehicles available. At the start of the project, I formulated an extension of a standard capacitated vehicle routing problem with time windows model. The objective function was to minimize the expected cost of travel distance and time spent between customers. Parameters included vehicle costs, capacities, customer demands and time windows, and the distances and times between customers and the depot. Decision variables included matrices containing the delivery quantities, paths traveled, and expected service start times. I also defined constraints to ensure that solutions are feasible. Customer demand must be met, vehicles must be loaded with the same number of pallets as they deliver, vehicles cannot deliver to a customer if they do not visit that customer, vehicles may only depart from the depot with a load less than or equal to their pallet capacity if they deliver goods at all. Vehicles must return to the depot if they have departed from it. Vehicles may only depart from the depot once each. Vehicles must depart from customers at which they arrive. The time at which a vehicle begins service at a customer must fall within that customer's time window. The difference in the times which a vehicle begins service at two consecutive customers along a route must account for the expected unload and travel times. After completing the model formulation, I implemented it in IBM iLog's Cplex Optimization Studio. This is a state-of-the-art software suite used for solving mixed integer and linear programming problems. It constructs its initial solution using root node processing, then applies the branch and cut method to solve problems exactly. Seen here is a small solved problem instance with the depot, customers, and vehicle routes depicted in the Cartesian plane. I verified the implementation by using it to solve similar small random test instances exactly. Here, the horizontal axis represents the number of customers in a problem instance, while the vertical axis represents the mean solution time in seconds. Note that the vertical axis is logarithmic. During this verification, the implementation exhibited exponentially increasing solution times, making the implementation unsuitable for application to realistically sized problem instances. In a bid to reduce the solution time while solving the problem instances exactly, I implemented in Python an algorithm by Vidal et al. Called the Hybrid Genetic Search with Adaptive Diversity Control. Originally published in 2012 and improved upon in a 2013 paper, it was one of the top performing algorithms presented in a survey and synthesis found in the second edition of Toth and Vigo's famous vehicle routing book. It was presented by Vidal as a powerful and versatile algorithm capable of handling a large variety of constraints. Here is a graphical representation of the benchmark results of Toth and Vigo's survey. The horizontal axis represents the normalized runtime in seconds, while the vertical axis represents the average gap from the best known solutions to a number of well-known benchmark problem instances. The desirable portion of the Pareto front is highlighted in red, while the HGS-ADC algorithm is represented by the red squares at the bottom. Vidal, who was listed as one of the contributors to this chapter, published an earlier survey and synthesis that looked at the common meta-heuristics employed by the high-performing algorithms considered. Taboo searches appeared the most frequently amongst the neighborhood-centered meta-heuristics, while the genetic or evolutionary algorithm was the most popular type of population-based meta-heuristic. Here you can also see the other popular meta-heuristics. The HGS-ADC algorithm functions largely as a genetic algorithm, maintaining a population of solutions that is iteratively improved by generating new solutions and culling weak solutions. It is a hybrid algorithm because it also applies an iterative local search on each newly created solution. My implementation deviated from the algorithm as described by Vidal in some areas. I chose to use a beta split algorithm presented by Vidal in 2016. In adapting the algorithm to be applicable to the context of the SPA Western Cape DC, I used the secondary chromosomes to represent the vehicle types rather than the depots and periods. I also derived and implemented my own customer completion procedure that properly handles split deliveries. The new split algorithm can process capacitated vehicle routing problem tours in big O to the n time for unlimited fleets, where n represents the number of customers, and big O to the nm time if a fleet contains m vehicles serving n customers. As part of the algorithm, a list of potential travel costs is maintained, and routes are created by comparing the attractiveness of each stop as a predecessor to the next. Although Vidal et al.'s paper described how time warps are used to penalize solutions that involve vehicles arriving at a customer after the end of that customer's time window, they did not describe how to determine the corresponding departure times. Although algorithms are described in other research papers for determining optimal departure times, they were deemed computationally too expensive for such a small part of the HGS-ADC algorithm. A greedy heuristic was therefore designed and implemented in which customers are served at the latest possible time. I verified the meta-heuristic implementation by using it to solve approximately the same randomized test instances solved by the Cplex implementation. The meta-heuristic returned many identical solutions, while its other solutions had costs acceptably close to optimality. Here, again, the horizontal axis represents the number of customers in a problem instance, while the vertical axis represents the mean solution time in seconds. The meta-heuristic implementation also exhibited exponentially increasing solution time, but less so than the Cplex implementation, making it suitable to be used to solve realistically sized problem instances. I finally performed a case study using historical routing data from the SPA Western Cape DC's 2019 archive. After some analysis of the average number of deliveries per day over the course of the year, I identified 3 days, a relatively quiet day, an average day, and a busy day, on whose data to base the case study. Information pertaining to the number of deliveries, delivery locations, vehicle routes, in-house and third-party vehicles, as well as demand volumes experienced on these 3 days are shown here. Some simplifications and assumptions were made when processing the provided data. The historical data shows some vehicles as loaded beyond their capacity, which can occur when the loaders combine partially full pallets. The meta-heuristic cannot handle this, and customers along these routes had their load minimally reduced. Sometimes there are multiple distinct customers, such as a TOPS and a Super Spa, that may be served with a single stop. These customers were combined to reduce the complexity of the problem. The average unload times per pallet were assumed to be 5.5 minutes, where geo-tracking data was unavailable. The expected travel times and distances between customers were retrieved only once from the Bing Maps API at the start of the case study, then used for all problem instances. Customer delivery windows, which are partially a mechanism to guide human schedulers to create more optimal routes, were ignored to allow the algorithm to explore a greater realm of possibilities. The values used for the fleet were similar to SPA's real values, but deliberately rounded. A cost penalty was applied to the hired vehicles, even though they are cheaper in reality, in order to encourage the algorithm to use SPA's own fleet first. The algorithm was configured to allow unlimited fleets, and when evaluating solutions, would assume that each vehicle could depart on a new route after arriving back at the DC, plus some wasted time, allowing vehicles to potentially serve multiple routes during the 24-hour period. The displayed table contains a sample of the routes generated by the meta-heuristic. The stops on each route are represented by the anonymized store names, while the loads are represented by the pallets delivered at each stop. The routes favored by the algorithm favor the larger vehicles more than the historical routing data, and would combine multiple historical deliveries to single customers into as few deliveries as possible. The meta-heuristic was used to evaluate the historical routing decisions for comparison to its recommended solutions. It found significantly cheaper routes than were retrieved from the archive data, with savings of 4 to 11% per day. One should, however, maintain caution when considering the savings reflected. The model is simpler than reality, assuming that the demand, travel time, and travel distance are deterministic, and that there will not be inefficiencies when attempting to execute the recommended routing decisions. For example, in the historical data for the high demand day, one store was delivered to 4 times without the vehicle being full for any of those deliveries. As easy as that is to mathematically optimize, there were real-world reasons for this to have occurred. In conclusion, I've performed the following steps in order to address the problem undertaken during this project. I formulated an extension of the CVRPTW. I verified the model via an exact implementation. I implemented the HGSADC meta-heuristic to solve the model. I verified the meta-heuristic implementation against the exact implementation, and I validated the meta-heuristic implementation via a case study. Thank you for your attention.